Okay, so today's video rather, we're going to talk about phase diagrams. So phase diagrams, we are looking at the phases of matter in a diagram. So specifically, we're looking at what states exist at a specified set of temperature pressure. So as such, we generally look at a pressure versus temperature. So that's the diagram. It is a pressure versus temperature. Okay. And how this differs from what we've already seen, which is a heating curve or cooling curve, is our heating curves are at 1 atmosphere. Our phase diagrams are at all sorts of different pressures. So heating and cooling curves are at 1 atmosphere, while phase diagrams are at many temperatures, at many pressures. Okay, so like I said, this is going to be pressure versus temperature. So let's think about our states of matter. If we have a solid, we would think that would be generally the most compressed state of matter with the lowest energy. So solids are going to be low temperature, high pressure. So if you have high pressures, you're generally dealing with solid. If you have low temperatures, you're dealing with a solid. If we have a liquid, we're usually a little bit higher temperature. Than our solids. And if we get higher in temperature, if we compress, we're going to maintain a liquid, so this is going to be high-ish pressure. Not necessarily a high pressure, but higher pressures than we would see with a gas. With our gases, we're looking at higher temperatures. So they're in close to the same temperature range as the liquids, but they're going to be low pressures because it is a very non-condensed phase. Okay, so keep that in mind when we are looking at this. And within our phase diagram, we're going to see several different things. So they include phase boundaries, so we've got, generally we'll see a solid liquid boundary, a solid gas boundary, and a liquid gas boundary. Okay, this liquid gas, that's the same as our vapor pressure curve that we see in the Classius Clapeyron. Right? And our phase boundaries, these are all when phases are in equilibrium. Okay. In addition to our phase boundaries, we will also see what's called a triple point. So this is where our the temperature and pressure, where all three phases are in equilibrium. Okay. Then we have what's called the critical point. This is a point where a liquid and gas have the same density, so they are indistinguishable from each other. Now, with this, above our critical point, we get what's called a supercritical fluid. So at a higher temp or pressure, we develop a supercritical fluid. Supercritical fluids have properties between that of a liquid and a gas. I'm just going to put supercritical fluid, SFC, gas, and liquid properties. So what we see is a liquid-like density, a gas-like viscosity, and these are supercritical fluids are pretty neat. They can effuse through solids like a gas and dissolve materials like a liquid. Okay, and within our critical point, we have a critical temperature and a critical pressure. The critical temperature is the highest temperature where we can have a distinct liquid phase. Critical pressure is the pressure required to liquefy a gas at the critical temperature. So, critical temp, highest temp for a liquid phase, and then critical pressure, pressure required at the critical temp to condense a gas to a liquid. Okay, so here I have what a phase diagram would look like. We have our three states of matter. We have our solid at the higher pressures, lower temperatures. Our gases at the higher temperatures, solids at the higher pressures, lower temperatures. Gases at the higher temperatures, lower, I feel like I keep saying this wrong. Solids at lower temperatures, higher pressures. Gases, higher temperatures, lower pressures, and then liquids right there in the middle. A little bit higher temperature, a little bit higher pressure. Okay, so here is our triple point right here. Here we have our gas, liquid, and solid all in equilibrium. We have the temperature and pressure associated with that triple point. And then we have our critical point with the associated critical pressure and critical temperature. Here, we really don't have any distinction between our liquid and a gas, but above that critical temperature and critical pressure, we get a supercritical fluid, that liquid / gas-like substance that dissolves, yet is very, not very viscous, so it diffuses as well. Very interesting. So these are all the different parts of a phase diagram you should be able to label. And you should understand how the different phases work. Like I said, solids, high pressure, low temperature, gas, high temperature, low pressure, liquid, mid. Okay. So most of your phase diagrams will look like this. One phase diagram that looks a little bit different I want to just point out to you guys is the water one. So here, real quick, if we look at our solid liquid phase line, equilibrium line if you will. So this is our melting freezing line right here. So this is the line that we would say that our liquid and our solid is in equilibrium. This is our vapor pressure line when our liquid and our vapor are in equilibrium, and then this is our solid gas line. So this is when our solid and gas are in equilibrium. So sublimation, deposition, evaporation. Over here we have evaporation and condensation, those type of things. So each one of these represents an equilibrium, and specifically this line right here, we see that we slope to the right. So as we increase our pressure, it takes a higher temperature to get to a liquid. Okay, we see a slope that is opposite in the case of water. Okay, so let's think about that for a second. With water, we have a slope where as we increase pressure, we're more likely to be in the liquid phase. Like if we stay at the same temperature, but we increase pressure, we're more likely to be in the liquid phase than in the solid phase. So I want you guys to think about that for a second. Why would having an increased pressure give us a higher likelihood of being in a liquid for water? And water specifically. There are probably other things that do this, reverse slope, but not very many. Okay, so as you guys may recall, or hopefully do, the liquid phase of water is a more condensed phase. Meaning that our particles are closer together in the liquid phase than in the solid phase, which is why ice floats, right? So because of this, when we increase pressure, maintaining a temperature will actually go to the more condensed phase of water, which is liquid. So this is just an anomaly, and I wanted to point that out to you guys. But make sure with these that you can go ahead and label all your states of matter, solid, liquid, gas, that you can label your state changes, melting, freezing, sublimation, deposition, vaporization, condensation, that you can write your equilibrium lines between solid, liquid, solid, gas, liquid, gas, and that you know where your critical point is. Here we're not actually showing the critical point, we're just showing the triple point. Oh, sorry, we are showing the critical point here and the triple point. So make sure you can show your triple point, I lied. We don't have a critical point on this one. We have our normal boiling point here. Here is where we have our critical. So make sure you can write where the supercritical fluid is, the critical point. And also, a thing that I haven't mentioned so far, something that should be a review from Gen Chem 1, but just in case. At 1 atmosphere, we should have what's called our normal boiling point. So 1 atmosphere gives us our normal boiling point. It's just normal because we are at that 1 atmosphere. So you should also be able to, at 1 atmosphere, determine what your boiling point and melting point are. So if I ask you for your normal boiling point or your melting point, you should be able to look at a phase diagram, go from 1 atmosphere, go to your solid liquid line, go to your liquid gas line, and give me my the normal boiling point and normal melting point. Okay, that's everything for this video and the end of chapter 11. You guys have a great day.